Okay, AP Physics 2. So we've completed our first unit on thermodynamics, and now it's time to talk about Unit 2, Fluid Mechanics. But what exactly is a fluid, though? Now, you should be familiar with this concept already. I can guarantee you've learned about it in a previous science class, but let's go ahead and go through the details. A fluid is ultimately a substance that flows. And really what we mean by that is that it's going to be able to move very amorphously. So typically we're talking about liquids and gases. And another way to kind of think about this very quickly is that it's a substance that takes the shape of its container. If we pour a liquid in a glass, for instance, the liquid changes to the shape of the glass. If we stick a gas in a gas cylinder, it's going to fill up and take the shape of the cylinder. Now, an important thing about this flowing, though, is that it allows us to really treat fluids, and we're going to go ahead and do this, as if they are a singular mass with no internal structure. So much like we did with solid objects last year, we can treat an object as though it's a single piece. We can treat the fluid as if it is a single piece. So we're going to be focusing on its macroscopic properties, not the microscopic properties of how the atoms are attracted to each other, how they move past each other, all those sorts of things. We're going to be looking big picture here. So why didn't we talk about fluids last year? Well, that's because their behavior can be unbelievably complex. As we can see here, this is basically some smoke that's had some dye added into it, so you can see its pattern as it flows a little better. And there are tons of these whirls and swirls, and basically it is extremely difficult to understand this mathematically. However, there are some steps we can take to make this a little bit easier. So we're going to be specifically working with what are known as ideal fluids. Okay, and ideal fluids have a few key properties, specifically three. The first of these is that ideal fluids are incompressible. And what we mean by that is, so for instance, let's say I've got a little block of fluid here, imagine this is a little cube of water. Well, the volume of this water is going to be consistent. Even if it changes shape, the overall amount of space it takes up is going to be the same. Now, granted though, if we have a certain mass of water here, and its volume is staying the same, if I push it, it's not going to change its volume at all, well, that means its density is constant too. And this really means that incompressible fluids are really only going to be liquids. We are not going to be dealing with gases in this unit. We're going to be working almost exclusively with liquids instead. So let's go ahead and pause there and talk about this property of density, which is something you definitely learned about in chemistry, but you probably abbreviated it with a capital D in that class. And in physics, we don't abbreviate that way. We instead use what this is, which is a Greek letter rho, R-H-O, pronounced like R-O-W, rho. And it looks a bit like a weird P, but whereas a P is pretty straight, a rho kind of is curved, almost kind of like a backwards 9. And density is the ratio of mass to volume for a particular substance. So the equation is pretty simple. Rho is equal to mass over volume, where keep in mind that V needs to be a capital V, because lowercase v is velocity, where the mass is in kilograms, the volume is in meters cubed, and so density is therefore in kilograms per meter cubed. Now, I want to be careful there, because in chemistry you probably did density in grams per centimeters cubed, which is totally fine, but in this class, and for all the equations we're going to be using, we need it in kilograms per meters cubed rather than grams per centimeters cubed. Okay, so keeping that in mind, what exactly does density really tell us? We can calculate it this way, but what it is really telling us is how compact the matter is in a certain amount of space. If we have a more dense substance, there is more matter crammed in. If you have a less dense substance, there is less matter crammed into that same amount of space. And because we're dealing with incompressible fluids, so this is really true for most solids as well, density is pretty much uniform throughout the object. So if you take a little piece of the solid, or you take a little bit of the liquid, you can determine its mass and its volume and its density, and that density should be the same for the entire solid or liquid, etc. Now, density we are going to use in many different contexts in this unit, but a really, really big one is the fact that it allows us actually to determine masses better. So for instance, let's say you have like a swimming pool filled with some liquid. Now, if I asked you to mass what was in that swimming pool, like how much mass was in there, that would be extremely difficult to do. Like you can't put that on a scale or something. But instead, what you could do is you could take a little chunk of that fluid out and you could determine its density using like a graduated cylinder and a scale or something along those lines. And you could measure the proportions of this pool so you could get its volume. So we could determine its volume and its density. And if we multiply that volume across, we could therefore determine the mass of this block of fluid. So really what I want to get you used to is that when you see this combination here, rho V, rho capital V, whenever you see these two variables next to each other multiplied by each other, you need to immediately be thinking, oh, that's the exact same thing as mass. We're going to use them pretty much interchangeably. So going back to ideal fluids, we just said the first property that they're incompressible. We can't push them in and change the amount of space they occupy, so the density is constant. The next thing is that they're going to be non-viscous. And what does that exactly mean? Well, viscous, that word right there, is related to viscosity, if I could spell it right. There we go. And viscosity we can think of as the thickness of a liquid. For instance, if you put your hand in a liquid and you feel a lot of resistance to your hand moving through it, that would be a viscous fluid. It's very thick, it's resisting you. So a non-viscous fluid is one that's going to have little resistance to flow. So for instance, a viscous fluid would be something like honey, molasses, syrup. A non-viscous fluid would be something like water, rubbing alcohol, various things like that that don't have that resistance. And that means that we don't have to worry really about friction either between the fluid and the container it's in, or really even between the molecules in the fluid. And lastly, the last property we have for ideal fluids is that, and this is really not going to come up in the first couple of lessons because we're going to be dealing not with this situation, but ideal fluids only have laminar flow, meaning that all of the fluid is moving in the same direction at the same time. Now, for instance, in laminar flow, if you had a pipe here, all of the water, for instance, in this pipe, would be moving in the same direction all together at the same speed. Turbulent flow, where you'll get these whirls and swirls in the liquid, and it'll start looping back on itself, and it gets way more complex, way more quickly. So we are not going to deal with this situation. We are only going to be dealing with laminar flow. As a general note, a great example of a pretty much near ideal fluid is water. So we're going to be using water in many of the examples in class because it follows all these properties and makes our life a little bit easier. Now, a very key piece of information you want, though, is that the density of water is 1,000 kilograms per meter cubed. Now, in comparison, in chemistry, you probably learned it was 1 gram per centimeters cubed. Good to know. But this is a number we pretty much, I would always provide it to you on like a test or something, but you really just want to memorize it, that the density of water is about exactly 1,000 kilograms per meters cubed. So now that we've established a lot of the basics for the unit itself, let's actually focus on this specific lesson, which is that of fluid statics. And by fluid statics, remember static means ultimately something that is not moving, meaning that we're going to be initially dealing with only something known as hydrostatic equilibrium. This fluid is essentially at rest. Like there might be a little bit of movement, but ultimately there's not a whole lot of flow happening. Now, we went ahead and already talked about density a good bit here because whatever we talked about density, that's really going to apply to the unit as a whole. But the rest of this conversation is going to be focused on pressure. And really, how we're talking about pressure today is really only going to deal with static situations. When we start dealing with flowing fluids, how we deal with pressure is going to end up changing. So let's consider a situation for a second. Let's say I've got 3 different containers of different shapes and sizes, and let's say I just put a nice solid object in one of these, like a little block, and if I look at that, if I was going to study how this block is like interacting with this container, I could be like, well, you know, the block is being pulled down by a force of gravity, it's going straight down, and that's pretty simplistic. And if I took this block and moved it to the different containers, I would see that force of gravity would be pretty much the same on this block in all 3 situations. But let's say we instead had, rather than a solid block, we filled up this container with some liquid. Let's say this liquid had the exact same weight, the exact same force of gravity as that solid block. Well, it's going to be still pulled down with that same force of gravity, but how it's interacting with the container is going to be a bit different now, because we're going to know that, all right, well, it's kind of pushing down some here, some here, some here, but it's also pushing on the sides of the container. And if you're not sure about that, like imagine if this side of the container just disappeared, well, the liquid would just flow right out of the container. So it's definitely pushing on all these different sides. And if we took this liquid and we poured it into these different containers, well, this would all be a little bit different in each situation, right? Like how they're pushing on the sides of the glass, all these other things would be different. So describing it as a simple force of gravity doesn't really encapsulate entirely what's happening here. So we've already learned about this concept of pressure, which we abbreviate with a capital P, because it's just the measure of how force is distributed over a surface. Remember, we're looking at the macro scale now. The unit is in pascals, and it's just a force over an area, or a Newton per meter squared. So a pascal is equal to a Newton per meter squared. Well, when we're looking at fluids in hydrostatic equilibrium, what really causes the pressure is the weight of the fluid above a particular surface. Now, while we're going to be primarily dealing with liquids, there's a very important point we need to bring up, which is that all of the liquids we're dealing with are going to be exposed pretty much to the atmosphere. So let's say you're standing on the beach here at sea level, and it's got fairly standard weather and temperature, etc. Well, there's going to be this weight of air from the atmosphere directly above you, pushing down on you, and all that weight is going to contribute to something known as atmospheric pressure, which we typically abbreviate with a capital P, lowercase 0. So that's really like P naught. And what atmospheric pressure is standard, like the average at sea level, is 101,325 pascals. Now that is extremely specific. So to simplify things, we're going to go ahead and just say that atmospheric pressure is equal to 1 times 10 to the 5th pascals. And that is, once again, this is on your equation sheet, but this is a number you want to be familiar with. And let's change the scenario a little bit more, and let's say that, one person is standing on the beach and one person is snorkeling here below the surface of the water at the ocean. And we already know intuitively, just in our everyday life and experiences, that the person underneath the water is experiencing a greater pressure than the person who is on the beach. And that makes sense because they've got more fluid pushing down on them. Both of these people have atmospheric pressure pushing on them. So for the person on the beach, the pressure they experience is only atmospheric pressure, 1 times 10 to the 5th pascals. And for the person underwater, there's that amount of air pushing down on them, the weight from that air pushing down on them. But additionally, they have this additional piece of water directly above them pushing down on them. And the weight of this additional fluid, this additional water, causes what is known as capital P lowercase g, or the gauge pressure. And we're going to come back to that a little bit more in a second. But the total pressure for the person underwater then is the pressure from the atmosphere plus the pressure from this additional gauge pressure, this additional fluid. So we already talked about atmospheric pressure, but what exactly is gauge pressure? Capital P lowercase g, like a little g subscript. Well, this is the pressure measured for a fluid by a gauge that has been calibrated to not include the contribution from the atmosphere. So let me go ahead and pause there and talk about what exactly that means. So imagine you have a tire gauge, right? And then you go and you stick it up to your tire, and you can basically push it against the little cap on the tire, and it'll tell you what the pressure inside the tire is. Well, when you have that tire gauge not pushed onto the tire, cap there, it's still experiencing a pressure. Pressure from the atmosphere is still pushing on that tire gauge, and you notice it's not shooting out and telling you so many pascals, though realistically ours would say pounds per square inch, but, you know, same sort of idea here. Well, that's because that atmospheric pressure is everywhere, and so the gauge has been calibrated to not measure that. It's only going to measure pressures above atmospheric pressure. So therefore, if you go to your tire and you stick the tire gauge up to it, it's going to shoot out and show you this additional pressure. We know it must be above atmospheric pressure because if you poke a hole in a tire, air rushes out of it because the air is trying to go from this high pressure region of inside the tire to the low pressure region of outside the tire. So that is really what we mean by gauge pressure, but a much more simplistic way to think about it is that it is the pressure from any additional fluid that is on top of that from the atmosphere. Now, how exactly do we calculate the gauge pressure? Well, let's say, for instance, we have like a surface of the water here, and let's say we're looking at this point right here below the surface, and we're looking at this particular surface area at that point. So if we want to know the gauge pressure, we would need to know the force of gravity, or the weight of this fluid right here in this cube, divided by this cross-sectional area. All right, well, with that in mind, we can remember that the force due to gravity is the mass of this fluid times g divided by a. And remember, we just talked about we can substitute in for mass the density of the fluid times this volume of the fluid. So we're going to go ahead and stick in rho v for m. Well, when we do this, well, what exactly is the volume here? Well, the volume would be this cross-sectional area times some height h, where height is really the height below the surface of the water, or in other words, really it's the depth. And so we have rho times a times h times g over a. We can cancel these a's out, and so therefore the gauge pressure is equal to rho g h when we rearrange things a little bit. So we had atmospheric pressure, pressure from the atmosphere, the weight of the atmosphere. We had gauge pressure, which is the from the weight of the additional fluid, and therefore we have this last thing known as absolute pressure, which is just with a capital P. There is no subscript here, and this is really the total pressure that is acting at some point. So you have to add the two previous pressures together. So this right here is equal to the gauge pressure, and it's equal to the density of the fluid, that is not the atmosphere, this additional fluid, in kilograms per meters cubed. G, which is the acceleration due to gravity, we can just use 10 meters per second squared. And this we have to be really careful with. H is the depth of fluid above this certain point. We're talking about from the surface of the fluid to this particular point. I know it's annoying that it's an H, that's just convention. And it has to be measured in meters to keep everything consistent. So before we wrap up, let's just talk about a couple of subtle points that are really good for us to start keeping in mind. Let's say we had here, for instance, a container that has some fluid like water in it. So some basic things is, first off, the pressure from this static non-flowing liquid at different points in the fluid is dependent on, one, the density of the fluid. So if we replaced this fluid with something more dense or less dense, that's going to change the overall pressure because you've got either more or less matter pushing down. But it also depends on the depth. So if I'm looking deeper in the fluid, this fluid down here has a higher pressure than the fluid up at the top. Okay, so that makes a lot of sense. Additionally, if we look at identical depths in the fluid, if I look at all these same depths, they're all going to have the same pressure. If I look at all these same depths at the bottom, they're also all going to have the same pressure. Now, one more final point to bring up, though, is that let's say we had a single point in the fluid. Does this pressure have a direction? And you might think, well, yeah, downward, right, because it's from the force. But really, the pressure is going in all directions. It's actually a scalar, not a vector, so it does not have a prescribed direction. And why would that be? Well, if it was downward, well, then that fluid would start moving downward due to the force, and it's not flowing, so the fluid must be pushed in from all angles with the same amount of force. And that would be the case at every point in the fluid. At this point, the pressure is the same in all directions. At this point, it's the same in all directions. Same, etc. But that means if we look at a point on the outside of the fluid, like right against the, let's say it's a glass container, right against the glass, it's going to have basically pressure pushing in all directions, but it also means that it's going to be pushing against the glass here, and the glass is going to be pushing back against it. But notice why I said it's pushing against the glass outward. And that tells us that every surface of the container, the pressure is going to be pushing normal to that surface. Remember, what does normal mean? Normal is the exact same thing as perpendicular. It's going to be pushing perpendicular to that surface. So at the bottom, the forces from this pressure is pushing downward on the container. On this right-hand side, the forces from the fluid pressure are pushing outward to the right, and on the left-hand side, it's pushing outward to the left. And you'll notice I made these forces get bigger as you go further and further in depth. And this makes a lot of sense, because if, for instance, you were going to come over to this container and like if you popped a hole in it right here, well, what would happen? The liquid would immediately start streaming out normal. Now it would start to arc down due to gravity, but initially it would shoot out horizontally here because the force is normal to that surface. So this is going to wrap up our conversation on density and pressure. So what are our main takeaways? One, can we identify and explain the properties of ideal fluids, aka that they are incompressible, that they are non-viscous, and that we're really only going to be looking at situations of laminar flow. Can we calculate and utilize the density of a fluid? Of rho is equal to mass over volume, and additionally, if you want to find the mass, we would multiply the density and the volume together. And lastly, can we identify, explain the cause of, and determine atmospheric pressure, gauge pressure, and absolute pressure? The cause is ultimately the weight of pressure above a particular surface. The atmospheric pressure is just from the weight of the atmosphere. The gauge pressure is from any additional fluid above a surface. And the absolute pressure is just the total pressure combining those two.